This is part 2 of the series Applications of Differentiation. We have an airplane flying at an altitude of 6 miles on a flight path that will take it directly over a radar tracking station. If S, the direct diagonal distance from the plane to the station, is decreasing at a rate of 400 miles per hour when S equals 10 miles, what is the speed of the plane? Now for this problem, I'm going to need a picture. So let's go ahead and bring up a picture of this situation. So here we have the plane, 6 miles high, and the direct distance from the plane to the station is labeled S. And I've gone ahead and labeled the horizontal distance from the plane to the station as X. So let's go ahead, try to characterize what they've given us. Aside from these distances, they've said that the distance from the plane to the station is decreasing at a rate of 400 miles per hour when that distance is 10 miles. So they've told us the rate of change of this distance here is decreasing at 400 miles per hour. So ds dt equals negative 400 miles per hour. And the reason it's negative is because it's decreasing. And what we're looking for is the speed of the plane. Well, since I've labeled this thing as x, the speed is going to be dx dt. So it's the rate of change of this distance here with respect to time. So that's going to be our speed. So we're looking for dx dt when s equals 10. Now to solve this problem, we have to keep several things in mind. The first thing that comes to mind here is that the plane is not flying along this path. The plane is flying horizontally. So that's the reason that this represents the speed of the plane. And so you can see that this right triangle is going to be changing dimensions. This side's changing and this side's changing, where we're considering the altitude as a constant. So we're relating this rate of change with this rate of change, and the only thing that we have to relate those two is this right triangle. So I think the best thing for us to do is go ahead and write down the Pythagorean theorem. So this squared plus this squared is going to equal that squared. So we know that s squared equals x squared plus 6 squared. So there's our equation that relates everything together. And now we have to get our ds dt and our dx dt. So clearly we're going to have to differentiate this expression with respect to time. So the derivative of this with respect to time is 2s ds dt equals 2x, that's the derivative of this, dx dt, and the derivative of this is simply 0. Now we're going to go ahead and substitute our values. We see that ds dt is 400 and s is 10 at this point. We have 2 times s, which is 10, times ds dt, which is negative 400, and that's equal to 2 times x dx dt. Now, we have a little bit of an issue here. In order to solve for dx dt, we have to have a value for x. So we see up here that s is equal to 10 at this particular instant in time. So this distance is 10. This distance is 6 miles. So we're going to figure out what this value is using Pythagorean theorem. So go down over here, and we know x squared plus 6 squared equals s squared, which is 10 squared. So x squared plus 36 equals 100. So x squared equals 64, and x equals plus or minus 8. We can ignore the negative, obviously, because x can't be a negative value. So our x value is 8. So let's simplify this side of the equation, which is negative 8,000 equals 2 times 8, which is 16, dx dt. And so finally, dx dt is equal to negative 8,000 divided by 16 is negative 500. And that's going to be miles per hour. So our interpretation of this result, the rate of change of x, this distance, per unit time is negative 500 miles an hour. That is, we're traveling this direction, negative 500 miles an hour. And now let's go on to another example. In this example, we have a television camera at ground level is filming the liftoff of a spacecraft that is rising vertically according to the position equation s equals 50t squared, where s is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. Find the rate of change of the angle of elevation of the camera at 10 seconds after liftoff. Well, as usual, I would like to draw a picture, so I'm going to go ahead and bring up a picture that I've already drawn. This is the location of the camera. It's 2,000 feet from the launch pad. This is the spacecraft lifting off, and this is S, the height above the ground. So let's go ahead and start characterizing our values and see what we can figure out. Now what we're looking for in this problem is the rate of change of the angle of elevation. So we're looking for the change in this theta value here. So it's actually going to be d theta dt. So the change in theta per unit time is what we're looking for. And we're given an equation that relates this height to time, but we don't have anything that relates this theta. So we have to come up with an equation that relates this value to the s value. And if you remember your trigonometry, hopefully, we know that this is the tangent function. I'm in the habit of using an old limerick for sine, cosine, and tangent. Some old horse caught a horse taking oats away. So we know that tangent of theta equals this height over 2,000. Now, it may appear that we can just go ahead and differentiate this equation as it sits, but if we do, we're going to have a ds dt, and we don't yet have a real expression for that. We have an expression over here that we can get ds dt for, but what we're going to do is we're going to substitute this expression for the s, the position of the spacecraft, in for this value. And that's going to take care of the relationship between this and the change in the angle. So let's go ahead and put that in. So we have tan theta equals 50 t squared. That's substituting this in for s over 2,000, which simplifies to t squared over 40. Now we can go ahead and differentiate this with respect to time. So the derivative of tangent is secant squared theta d theta dt. equals 1 over 40 times 2t. Now there's no implicit differentiation here because t matches the variable of differentiation. So now we're going to solve for d theta dt. So we have two t over 40 secant squared theta. Now to solve this, we need our t value, and our t is 10 seconds, so we can plug that in there. However, we have an issue here with the theta. We're going to have to determine what theta is at t equals 10 seconds after liftoff. In order to do that, we're going to need to know this s value. So we're going to have to take that time value, place it in this equation, and find out what our s value is. So we have s equals 50 times 10 squared, which is 5,000. Now, considering that that's 5,000, to find this theta, we know that this is tangent, so we know tan theta equals 5,000 over 2,000. And to solve this for theta, theta is arctan of 5 halves, because the zeros all cancel out there. This is going to give us approximately 1.19 radians. So that's what our theta is. Now I'm actually not going to use this value. I'm going to use the value that's stored in my calculator because I don't want to lose all this precision. So I'm just going to store that 1.9 decimal in the calculator and use it in the next equation. So let's go ahead and put that in here. So let's go up to the top, and d theta dt equals 2 times t is 10 over 40 secant squared 1.19, because that's my theta. Now I know that secant is simply 1 over cosine. So if I simplify this, I actually have 1 over secant is actually cosine. So I know this simplifies out to 20 cos squared 1.19 all over 40. And when I put this in the calculator, I get approximately 0.068997, which comes out to 2/29 radians per second. That is the rate of change of the angle of elevation of this camera as it captures the liftoff of the spacecraft. And now let's try one more example.